Hi and hello everyone. What we will see next is this particular queuing type systems which are called as queues with finite input source, right. What is the difference? That in all the models that we have considered so far, we have assumed that the calling population, meaning that the population from which the arrivals are to occur, it is infinite or it's large enough that it doesn't make a difference to the arrival rates, right. So it's large, quite large. That's what we have assumed. Okay. So that's what we say. It's a calling population. That's from the population from which the customers arrive to the queuing system, right. So we assume to be infinite technically, but it's large enough is what proper way to describe that. Okay. But there are systems where the calling population is finite. In fact, every calling population is finite. Because of largeness, we assume that to be infinite. But there are situations where it is, the size of the population is very minimal in comparison to the number of servers or something that we are considering into that. Okay. So, and hence the future event occurrences are functions of the system state. Naturally that comes into that mode whenever this calling population is finite. Okay. So, a typical application of this model or a typical example of this model is what we call it as machine repairment problem, so that you can understand the context. But this same context can be applied in many different situations where exactly similar kind of things can happen. Okay. Machine interference problem or machine repairment problem. So, what we have here, assume that we have C servers, the server here are the repairmen, okay, and they are available to repair or to take care of what we call m number of machines, where this m is greater than or equal to C is what we are assuming. Okay. Service times, meaning here the time required to repair a machine is distributed as exponential distribution with parameter mu, and the time for breakdown, which means the lifetime of the machine or the working time of the machine rather than the downtime of the machine. Working time of the machine is exponential lambda. So, there are machines which works for an exponential lambda amount of time, then it fails, and whenever it is the repair is started, the repair time duration is exponential with parameter mu, then the machine becomes up and so on, right, to this situation. So, the number in the system here corresponds to the number of broken machines, right. There are failed machines out of the total number of m machines. So, there are m machines, there are C repairments who take care of this, and whatever we described so far is what is exactly happening here. So, this particular thing, right. So, because of this exponential distributions in both, right. So, you have the transition rate diagram for this finite source queue could be written like this, right. So, 0 here means 0 broken down machines. So, there are m machines, each of them can fail with the rate lambda. So, the total rate with which an arrival happen to the system. The system here means the repair facility. An arrival happened to the repair facility means that one machine has failed, right. So, a machine has failed. So, that is what. So, from 0 the system will go to 1, which means to one failed machine with the rate m lambda, because there are m machines which are in operations, right. Similarly, when there is already one machine in the repair facility, so the remaining n minus 1 are in working condition, each of them can fail with the rate lambda, and hence you have the total rate of failure is m minus 1 lambda, because any one of these m minus 1 can fail. So, the minimum of exponential, which is basically m minus 1 times lambda, is the rate that you are having it here, right. So, this is what you have it as the rate of the birth rate in a way from state 1 to 2, right, and so on, everything you have it all the way up to this. When this state m means all the machines have failed and there is no more machines which is in working condition, so to fail. So, this ends here. So, this is a finite state BDP, and As usual, the service rate or the death rate for this BDP is 1, the C servers. So, up to C it will be mu, 2 mu, 3 mu up to C mu, but beyond C, like, so here this is the situation, these are the states in which there are some machines which have failed, but they are not being attended to by the repairman because all the repairments are already busy. So, they are in the queue. So, these are the states C plus 1 onwards up to M denotes the queuing component, right. There is a machines which have failed, but they are not yet being attended to by the repairman, and hence they are in queue. That is what the situation that you will have. So, this will be the rates as C mu, right. So, this is what is the scenario that you have here. Now, when calling population is large, we mean this M is so large that this M lambda or lambda, right, the rates in a way, all these rates are they do not have too much of impact. Okay, you still have whatever, because this M is very large. So, you have some rate of customers for coming to the system. So, this M or M minus 1 or M minus 2 does not make a difference to the arrival rate. That is what is the scenario when the calling population is infinite, but here it is finite. So, obviously, this in comparison to C, basically when we talk about this in comparison to C is what then we have to look at it. So, that means that these quantities do play a role. So, M, M minus 1, M minus 2 will make a difference, and hence you will have this kind of models that you have. This is what is the finite source model, BDP models, which is you can always remember with respect to this kind of situation that you have it in mind, machine repairment. So, this could be in many different situations, this can come, like there could be a fleet of say C cars with M drivers, right. So, the drivers can come at this rate, and then they can be using the car or act as a driver for an exponential amount of time. If you assume, then exactly same thing happens, and so on. There are many situations which you can fit here. So, as we see, this is the BDP, finite state BDP with now state dependent rates, right. So, both of them, right, arrival as well as are the birth as well as the death rates. So, this is the rate. Once we determine the rates for this, done. Now, like you can obtain in the usual manner the stationary state probabilities to be this quantity for n between 1 and C, and C n between C and M as these two expressions with R in the usual way as lambda by mu, which you can write it as in this form. So, this is basically MCN R to the power n P naught for n lies between 1 and C, and MCN n factorial C to the power n minus C factorial times R to the power n P naught for n lies between C and M is what then you will obtain as the steady state probabilities. Now, these are not in a very nice form for easy amenability. So, what you can call this whole coefficients here, you can call as something like an AN, right. So, basically the coefficients that is appearing in front of this P naught here in the expression for Pn, if you denote it by An, that means we are basically saying Pn is some An times P naught, where Ans are given by these expressions, depending upon whether n is lies between 1 and C or C and C to M. Then my P naught would be equal to 1 by this. This is only for ease of notation. I mean, just that we are giving another notation to these quantities that we have here. So, P naught would be by using the normalization condition that you will obtain P naught to be this quantity, right. And once you have that, then you can get the other performance measures, which is basically the first one is the average number of customers, which is L, which we know as equal to this, which is now in terms of AN you can think as this. Now, to obtain LQ, WQ, we first have to find the usual effective arrival rate into the system. So, the lambda effective is given by this quantity, right. So, this quantity, which if I use this L here, right, this n times Pn is occurring. So, I can use this L business here. So, that will be equal to lambda times M minus L, right. So, this is L is the average number of customers in the system, meaning the average number of failed machines, right, and M is the total number of machines. This is the average number of working machine. So, lambda is each one of them. So, this is what is the effective arrival rate is turning it to be, as one would think intuitively. Now, once we have this lambda effective, then LQ in the usual way you can obtain it as this using this expression, and W using lambda by L by lambda effective, and WQ is LQ by lambda effective, and so on, right. So, this is in the usual way you can obtain the performance measures for this particular. Now, for this C is equal to 1 case, right, you can see that the expression for this state probabilities becomes something like this, and but the rest of thing is that the expressions are slightly simpler form, right, the expressions are in a slightly simpler form, but analysis is similar, right, when single server case, but we can take in general the C server case as well. Okay. Now, there is an important invariance result for this finite source queues as well. Wherever possible, we always look for some kind of this kind of robustness properties or invariance properties. Okay. Here, what is that? So, the steady state distribution is valid, whatever the form that we have obtained, something like these for one server case, or the in general for the C server case. It is valid for any finite source system with exponential service. I mean, the service duration is exponential, or repairing duration is exponential, independent of the nature of distribution of time to breakdown. We have assumed the time to breakdown is also exponential, but it need not be. It can be even any general distribution, right, as long as the lifetimes are independent with mean 1 by lambda. As long as you have an independent, the one machine's failure does not affect the other machine's failure or breakdown. If that is a situation, and what it matters is only the mean rate 1 by lambda, right. The distribution really does not matter, which is a quite good invariance property, because the working time of the machine, now I can assume to be any distribution, still this same results will hold, right. That is what it means. Now, when C is equal to M, meaning that the number of servers is, or repairment is exactly equal to the number of machines, then the repair distribution can be G. I mean, repair distribution can be any general distribution, as long as now you require that failure times to be exponential. That cannot be. So, one of them you need this Markovian nature or exponential nature. In the general case, right, the Station distribution is or holds true independent of the distribution of time to breakdown, right. That is a more crucial one. But when this is happening, then the other side, like, but you need to keep this failure times are exponential, I mean time to breakdown are exponential, but the repair distribution could be general only in the case of C is equal to M, right. That is what. So, the first one is what is most crucial and most important from the point of view of applications or practical situation that you might have, right. Okay. So, that is the invariance property that you have for with respect to this. Okay. There could be generalization of this particular finite source model from to many different angles. The simplest and the simple generalization is the one where you are also assuming some spares are available for the machines. Okay. You have M machines, but in additional there are Y spare machines are also available. When any one of them fails, then the spare can come into play for the operations to continue. In the meantime, the failed machine can be repaired. So, this is if you assume that Y number of spares are there. Okay. So, at any given time there are at most M machines in operations. Okay. So, the rate of failure is at most M lambda, right, because spare machines is not being in operating condition if it is not required to be. If M is machine, if less than M, then only a spare machines start its process. Okay. So, that is then the rate, the birth rate for this particular situation would be this, right, and this for depending upon whether n is between 0 and y to y plus m and n greater than or equal to y plus m. So, the state now would go all the way up to y plus m rather than m. So, 0 to y plus m is the number of states in this particular BDP, and mu n remain the same, there is nothing. So, only the arrival rate there is change because of this pairs, and the number of states also would increase. So, this model exactly in a similar way can be analyzed, but only thing is the expression will get a little bit more trickier because of this expansion or different rates at different points, the state dependent rates that come into the picture. Otherwise, the analysis can be done in a similar fashion. That is what you can see. And this is a simple example, like whatever we talked about, what kind of questions that can arise and how one can get the things using this machine. Suppose assume that there are 2 workers who are responsible for 10 machines in a factory. Machines run on the average for 20 minutes and then require an average of 5 minutes of maintenance service, both times being exponentially distributed. Okay, as we say that there is invariance property which we can assume for the first quantity, right. We need not assume this to be exponential, but we still assume to be exponential no matter. So, this then the lambda is 1 by 20 and mu is 1 by 5 per minute, then r is equal to 1 by 4. We can compute first P naught. How do we compute P naught? First express this A1, A0, A1, A2 and so on. From that, using that you can compute P naught to be this, then we can get this L to be this much, which represents the average number of machines under repair. Then that means that m minus L, which is coming out to be 6.83, is the average number of running machines. So, the expected downtime, if you want to compute, of the machine that requires repair is 9.28. These are all certain measures that you can get. So, now you want to see, like you want to look at the system whether for improvement perspective or otherwise, like you want to see, like suppose for example, you can try this exercise, compute the average fraction of idle time of each worker. Okay. When P naught is, there is 0 machine, both the workers are free, and when 1 means state is in 1 means there is 1 failed machine. So, there are 2 workers here, right, there are 2 workers here. So, each of them can in an equal probability manner, which is 1 by 2, can be busy or free, right. So, that is what. So, the fraction of time, ideal time, the average fraction of ideal time of each worker is then would be equal to this quantity, right. Now, you can compute this to know how much time or how much proportion of time each worker is being idle. Now, that would can tell you, like suppose if it is very high, it may be time to add one more worker. So, now like if we add one more worker, what is going to be the impact? You really do not need to put that worker and then see what is happening. So, you have the model now, you can simply increase from 2 workers to 3 workers and see what is the impact on the average number of failed machine and how long it takes, what is the downtime of the machine, right. So, you can take all these things you can compute and then make a call whether to increase the worker or not. So, you can like this, like you can use your analysis whatever you have done with respect to the requirement that you might face to answer certain questions related to this. So, this is a typical example that you get. So, all these things, like you can, once you have the expression, then you can compute this very easily and then you can get the answers to whatever question that you are looking for. Okay. Right. Now, there is we can also look at waiting times in such finite source queues, because this is also little relevant as compared to the other cases. In some cases we never bothered about it because it is more similar to the other, but wherever there is some differences might come, we look at here. Now, here observe that an is not equal to Pn. An Pn is what? An is an arriving customer finds n in the system, Pn is at an arbitrary time there are n in the system, right. These are the probabilities that we have used. For this general finite source, we always assume that finite source queues without anything, if we say, it always means the one without spares. Okay, we never, if it is with spares we will specify, but we will not worry about that, we will always consider only the one without spares. Okay. So, which is a machine repairment problem without spare case is what the general finite source queue, for which this is not equal to true. Now, much like the MMCK case, we can derive the arrival point probabilities an in the similar way. It's exactly same expressions, right? An is what is it? What is it? It is probability of finding n in the system when at the point of an arrival of a customer, right? Using Bayes theorem, again this can be written in this form. Use Bayes theorem, you can write it in this form, where arrival about to occur when n is equal to 1 is basically this is the rate, right, as we know, and Pn is the probability that finding n in the system, right. So, this limit is what will be this. Now, again this quantity is simply m minus L. So, this is what is the probability. So, An is not equal to Pn, but An equal to this quantity, right. So, an interesting side fact here is that this quantity, which is what it says is that the arrival. So, if I think this arrival point probabilities and general time probabilities as a function of the number of machines. Okay. So, this one, which is basically the arrival point probabilities with m machines, is equal to the arbitrary time probabilities with m minus 1 machines. Okay. This is not necessarily true for the system with spares, but without spares, which is what our system is, this is true. One can prove that. Of course, we will also going to see prove in another context here itself. So, then once we compute this an, then this is routine ftq of t, which is the waiting time distribution of the waiting time in q, which is equal to this. So, there is 0 wait and there could be wait. The wait can happen only if the system is from at least C customers or BC, right. So, then exactly same argument. Then again you see that this kind of results we have already used in MMCK, that is why we are referring to MMCK model, right. We have used this quantity and this integral can be written as a sum, and finally we will arrive at this expression as the waiting time distribution. You can just work through and see that this is exactly following the MMC pattern that you are seeing it here, right. So, this is all about finite source queuing model. Okay. Next, what we will see is again a loss system, which is called as Engset loss system. Okay. But this is a finite population version of your Erlang's loss system, and it is named after Engset, who is a Norwegian mathematician and engineer. Okay. And effectively, like this he has given before Erlang, like in 1915 he had given this kind of it was available, but it was not published by then. Okay. Does it matter? So, this is basically the finite population version of Erlang's loss system is what then you. So, you still have C parallel servers with no waiting customers, but now we have a finite population of arriving customers. That is what we have the situation. So, basically what we have here is the system is then can be modeled by a BDP with rates as this, right. Remember, as opposed to your MMCC model, MMCC everything we had lambda, lambda, lambda. Here we have this finite source population model version of that. So, you have this state dependent rates here, whereas this death rates are the same as an MMC model. Okay. So, this is same as the MMC model, MMCC model, that MMC loss systems, and whereas the birth rate now is because of this finite source population, right. This is what here. Again, this is also like both the loss systems together is what is very critical for the teletraffic theory, or when you are trying to have a model. If it is infinite source population, then one would use the Erlang's loss formula, and when it is a finite source population version, then one would appeal to this Engset loss system, right. So, that is why this is together with respect to the loss probabilities or blocking probabilities or anything loss system model that you consider, both these models are very much important. So, and this is the finite source population version. So, the transition rate diagram for the Engset loss system would be given by this. So, it is m lambda when there is 0 in the system and so on. So, this is what is the version, this is the rate, then you can the usual way you can obtain the stationary system state probabilities using our standard iterative procedures, so which will give you this will turn out to be this quantity mcn r to the power n p naught, as you might expect from the case of this itself, the previous model, the finite source queue model. But now like there is no queuing happening, so that beyond that C server component the things are eliminated. That is what you have it here, right. For n is equal to 1 to C in terms of P naught, now the normalization condition will give you what is this quantity P naught, and P naught is turning out to be this, which is a truncated binomial distribution, because you can write it this quantity in terms of this, right. So, in terms of this for certain P and certain Q n and m minus n. So, this is a truncated binomial distribution, truncated to 0 to C. If you let this n running up to capital M, then you will get a full binomial distribution, but now you get a truncated binomial distribution. So, this is a truncated binomial distribution is what then you will get as the stationary or equilibrium system size distribution in the case of an Engset loss system. Now, once we have this, of course, then you can usual performance measures we can obtain, but we will concentrate only on one performance measures here, which is more important and which is different from the case of your Erlang loss model. Okay. So, which is the blocking probability concept. So, now as we said earlier, in the case of Erlang's loss system itself, like there is this notion of two types of blocking, one is time blocking, the other is call blocking. Here also what is this time blocking concept is that the probability that all C servers are occupied at an arbitrary time, which is also equal to the fraction of time that all the C servers are occupied, right. And this would be equal to PC, much like the earlier case, because the underlying Markov process is stationary, because of the stationary Markov process, because we are looking at an equilibrium distribution, right. Because of that, this probability is equal to the equilibrium distribution, which is given by this PC here, right. So, this time blocking probability remains as exactly same as the one that you would encounter in the case of an Erlang loss system, but the call blocking the notion would be varying now, because there the call blocking probability also was equal to PC in the Erlang loss model, but here the call blocking will not be equal to this. The reason is what we will see now. So, in the Engset model, the call blocking probability, what is that? The call blocking probability is the probability that an arriving customer finds all C servers occupied. This does not equal the time blocking probability PC. So, the time blocking probability remains as PC, but this call blocking probability is not equal. This is because the arrival process is no longer a Poissonian arrival process because of the state dependent arrival rates, and hence pasta does not hold here. Since pasta is not true here, so this call blocking probability is not equal to the time blocking probability, which is remains as PC. So, PC remains as in one sense one kind of requirement, which is the time blocking probability, which gives you the probability that all C servers are occupied at an arbitrary point of time. This comes from the notion of stationary distribution, the limiting distribution, and the fraction of time the all C servers are occupied comes from the notion of stationary distribution, since these two are one and the same in that particular case. So, and that is also equal to the equilibrium distribution's corresponding probability, which is PC. No problem. Erlang loss system, Engset loss system, both behaves in a similar way. But as far as call blocking is concerned, this does not equal because pasta property is no longer true here, okay, right. So, what is then that the probability? So, for which you want to see what is AN here. AN is the probability that the system is in state n upon an arrival. An arrival point probabilities is what this AN is, right. Then this AN turns out to be in terms of Pn, if I write, it is what this quantity is, which we have already seen it in case of finite source model, right. So, the proof, of course, you can see here that if you consider long period of time t, and during this time the average time spent in state n, right, this is the length of t. So, is p n t, right, because this is what is the fraction of time that you would see the system is in state n. So, p n times t is the average time spent in state n. Now, during this time, again during this time of t, the average number of arriving customers who find the system is in n is this quantity, right. So, the rate system in n is p n and m minus n lambda is the rate and t is the duration on which you are considering. So, the average number of arriving customers, the rate means without this t. So, the average, if you multiply by this, then you will get the average number. So, average number of arriving customers is this quantity. Now, what is the total number of arrivals during this? You have to sum over all possible n here, that is what this quantity is. So, the ratio will give you the arrival point probabilities, that is what you get here, right. It can be shown just like you just substitute p n, the expressions from here, right, this expression you just substitute into this one, right, you will see you will arrive at this quantity, right. So, writing explicitly the dependence, right, if you look at here, then this is what it is essentially p n with m minus 1, right. So, a n with m is equal to p n with m minus n. We observed in the finite source Q model, and that is what is the case in this particular case is what relevant. So, what does that mean? That an arriving customer sees a system where there is one customer less, possibly excluding himself or herself in equilibrium. That is what is the representation here. Now, once we have here, now we can talk about the call blocking probability, which is basically this one. The probability that an arriving customer finds all C servers are occupied would be given by this, right, when there are m customers. But we know that this is equal to this, so it is P C with m minus 1 customer, which is equal to this quantity, right, where the original P C with m had m here and here the arrival point probabilities, right, this P C a n a c of m is equal to P C of m minus 1 is what we have observed. So, that means a c of m is what we wanted. So, that is equal to this quantity, and this is what is known as Engset's blocking formula. As opposed to Erlang's blocking formula, the Engset's blocking formula refers to the call blocking probabilities, because this is what is of interest. When a call comes, what is the probability that it will be blocked, right. So, this is what is relevant here, right, not exactly P C, which is still a blocking probability, but it is a time blocking probability. But what is more important is the call blocking probability, which is this quantity, an arriving customer finds all the server B C, right. That probability is given by this, and hence this is the Engset blocking formula. Okay. So, what we have now for the Engset model, the call blocking probability in a system with m customers equals the time blocking probability in a system with m minus 1 customer, right. That is what you are observing, and this is the most important formula as far as this Engset model is concerned, which is the blocking probability or Engset's blocking formula or the last one. Okay. Now, like other performance measures like L etc., we can compute in the usual manner, right, after computing the effective arrival rate. As I said, a typical application of the Engset model is on the telephone traffic modeling in access network. So, you have, for example, assume that a potential users of a link is moderate, say a closed group of office network or some such thing, where customer is basically here the calls. So, lambda is the call arrival rate per idle user, and 1 by mu is the average call holding time, m is the number of potential users, c is the link capacity. Now, a call is lost if all C channels are occupied when the call arrives, and the Engset block formula gives the probability of such an event. Okay. So, now the objective could be in this case to decide C such that this probability is bounded, say at 1% or so. So, you have to determine some. So, this is what you might see, like in a closed network, you want to determine what would be the link capacity and the number of channels to be put in the link, so that whenever a call is made out of this finite population people, a call is made, that the blocking probability are not able to connect, the probability of that would be bounded by certain quantity, say 1%, 5% and so on. Okay. Another application, as we already pointed out, is a taxi service system with a certain number of taxis and certain number of operators for the taxi, right. Like this, you can think about many other different uses of for this. So, this is the Engset model, Engset loss system model that you have, which is both the loss system together is what the loss systems which we have. The main difference is the blocking probability idea between these two, and that this Engset formula is also very much used like this Erlang's loss formula in reality. You can browse it and you can find it out. Okay. So, what we see next is queues with state dependent service. Okay. So, what is that? So, this is the what we have a situation. So, the mean service time now is dependent on the state of the system, which is basically the number in the system. So, the simplest model one that one can think about is has, say for example, a two service rate, a slow rate and a fast rate. Okay. So, work is performed at a slow rate until there are k in the system, at which point there is a switch to the faster rate. Maybe there is a machine which you can tune it to a faster rate once the number of customers is reached at least a certain number of points, which we call it here k. Okay. With the usual assumptions, right, the mean rate now will be that mu n equal to mu 1 up to k, and it becomes k from the moment. So, where we assume that mu is a faster rate than mu 1. Okay. Now, again assuming arrival rate will be Poisson with parameter lambda, like a simple MM1 situation, we have MM1 situation, but with two service rates. Up to certain states it is one service rate, and beyond that it is another one, right. So, your Pn in the usual way you can obtain it to be this, with rho 1 as lambda 1 by mu and rho as lambda by mu. We can denote it, compute it to be this, right, for n greater than or equal to k or n less than k, the Pn's. Now, the normalization condition will give me what is this P. Now, again this part is finite, and this part you can take this out and you can take one rho to the power k minus 1 out. Then what you would see is that it is geometric series with rho. So, for rho less than 1, that will have the solutions here, right. And but rho 1 can be anything, but rho 1 is not equal to 1 and equal to 1 case, so you will get little simplification here. And for rho less than 1 only, this series would be convergent, and that would be the condition for the existence of steady state solution even in this particular case, right. So, then P naught is given by this. Once I have P naught, then I know Pn's is in terms of P naught in this form. So, you can still handle it. So, you can compute the expected Q size with rho 1 not equal to 1 we are given, with rho equal to 1, this is much simplified version of this. So, which is basically this quantity, which is again in terms of P naught we are writing it in terms of this. So, this is equal to this directly. Now, this quantity and this quantity you can simplify it using your this is basically a geometric series, this is a finite sum. So, we assume that rho 1 not equal to 1. So, you can get this term and this term as by simplifying these quantities. So, this will turn out to be the expected Q size which we are writing in terms of P naught for the case rho 1 not equal to 1. For rho 1 equal to 1, you can obtain similarly, there is no problem. Now, once we have this L, then LQ you can obtain it using this particular relationship that holds for single server queues, and W and WQ from L and LQ you can obtain it using Little's law. One thing that you note here is that this relationship W is equal to WQ plus 1 by mu is not true here, because this mu is not a single mu, but it is depends on the system state. So, here there is only one switch, right, a point k, but because of that is not true, but from these previous equations you can observe that W is equal to WQ plus 1 minus P naught times lambda. So, that means the expected service time is essentially 1 minus P naught by lambda, which is originally like you would see it is 1 by mu, that is what you might see. So, that is what you would see, this is a slight variation that you are seeing in this particular model, but otherwise your process was similar. So, here what we have a system, right, which is state dependent service. So, we have basically at one time switching off service rates. So, this simple model can be generalized to a C server version, right, with a rate switch at k greater than C, right, because it does not make much sense if you switch the rate beforehand. Maybe you could have, that is a different matter, but at least a simpler version. Now, another generalization could be to have 2 rate switches, then you have n rate switches, 10 rate switches, anything you can think about it, like all these things can be simply thought. This is only like you are switching rates at certain time points, meaning that once the system size is this much, then I am going to switch to another rate. But in extreme, another possible type of model is the one where the mean service rate changes whenever the system state changes, right. So, it could make it continuously dependent on n. For example, we can assume in a single server Markovian state dependent service model where mu n is n to the power alpha times mu. So, this gives us this as the right, the Pn's in terms of P naught, where P naught is given by this. Okay. But now, if you look at it, this infinite series converges for any r as long as alpha greater than 0, but the closed form expression you can obtain only for alpha equal to 1. So, what is then the alternative? So, one could use some numerical procedures to compute P naught, and once you have this, then other performance measures also you can compute numerically. So, you see here the models, even in a bottleneck scenario, if you have some such rates, if you are going, then immediately the analytical tractability of the model might be lost, but still you can employ the numerical procedures to get the solutions, right. So, this is state dependent service thing here that you have here. Okay. Next, what we will see is basically, of course, these are not the only service dependent case. So, there could be many different ways in which the muons can depend on the state. Okay. Next, what we will see is the queues with impatience. It is as important as the arrivals and services, because for a system operator, system manager, this is very important, like what is the customer feels about his weight in the system, so that he can act accordingly. So, that can be brought in only if you bring in some sort of this impatient behavior, right. So, customers are impatient. When do we say that? If they tend to say, for example, join the queue only when a short wait is expected, or even if they joined and they tend to remain in the queue if the wait has been sufficiently small, right. But the longer waits either at the time of joining or after while waiting in the queue, if they see, they might be tempted to leave the system. So, that is the phenomena that we are trying to see, the impatient capture. So, it is as important as arrivals and departures, because it gives an indication about what the customer feels, so that the corrective actions can be taken. We look at this very simple model, very simple settings only, but this is applicable to a more general setting, which we are not going to see anymore from now onwards. Even when you look at the more general Markovian model or semi Markovian model, wherever it is, right, because this itself becomes a very large class of models, that any model that you have, you can always bring in an impatient component inside. You can see how that impatient component comes in, that is all you can observe, and that is applicable across different models. Okay, that you have to always keep in mind, because we are not going to revisit in an explicit manner the impatient behavior in queues later on. Okay. Even here also we will see how one can handle, that is all we will see. But we have three basic forms of impatience, right. One is called balking, the other is reneging, third category is jockeying. First we will talk about balking. So, let us take an MM1 model with balking. Okay. So, you have already specified the model MM1. So, it can be applicable to MMC, it can be applicable to other forms, finite server, anything like you can always incorporate this balking. But what we are seeing is a simple scenario. So, the arrivals become discouraged when the queue is long and do not wish to wait. So, basically the bulking here, we are looking at the queue size, and the queue size determines the bulking nature for the arriving customer. So, even MMCK model can fall into this category, but here it is a sort of very artificial in a way that all customers bulk when there is K, when the system is full. Okay. They have exactly the same behavior, but if you think that way, then it is also falls into this bulking, right. But it is a rare phenomena to be exhibited by all arriving customers. So, that is why we may not call that in that fashion, but in one way if you think, this also falls into this category. So, one approach to model bulking is to employ a series of monotonically decreasing function of the system size multiplying the average rate of arrival. So, you have this rate of arrival lambda, which is what you assume, for example, in a simple MM1 situation. Now, what you do is that you multiply by this function Bn such that these Bn's are between 0 and 1 and they are decreasing, right, because more in the system size, the less would be the arrivals, right. That is what you want to see. So, that is why it is a decreasing function of system sizes that you want to have, with starting with B naught equal to 1, right. So, now when C is equal to 1, then that means this is our usual expression for Pn. Now, this turns out to be this particular case. Now, basically you need to worry about the handling this particular quantity to handle this, to arrive at this Pn, and hence the complete steady state distribution. Once you have that, then you can obtain the other performance measures and so on you can do. Some useful forms for the discrete functions which meets our criteria are say 1 by n plus 1 or 1 by n square plus 1 e to the power minus alpha n etc., etc. Like these are some of the forms, and of which this particular form is most important, and that is the well known Q which is called as the discouraged arrivals Q. Even others also discouraged arrivals Q, but this is the most standard form of the discouraged arrivals Q is basically with the birth rate of. So, if I plug in Bn equal to 1 by n plus 1, then what I have here is lambda n equal to lambda by n plus 1 is what is the arrival rate, and mu n remains as mu in case of this particular scenario, right. That is what is the rate. But in that model is important for one other reason. The reason is that the stationary distribution for such a model, if you compute, it will turn out to be this particular distribution, which is Poisson with parameter r. But you see here, this was also the stationary distribution for an MM infinity Q, right. So, what does that mean? That in equilibrium, these two models behave in a similar fashion, but their transient behaviors are different. So, that could be one of the reasons why you want to look at the transient behavior, not just the equilibrium behavior. And also, though this one is the case, the other performance measures like also would be different, right. You would see what will be L, LQ, W, WQ in each of between these two models itself. Though this distribution remains the same, right. You would see that they are might be different as well. That is what and there is a queuing happening here, whereas in that MM infinity there is no queuing happen, queuing does not happen, right. So, you also have to remember the differences. So, but this distribution alone does not tell you everything, the nature of the system also you have to keep that in mind. Okay. Now, this is one way of discouragement is based upon the number in the system. Another way of discouragement for a customer bulking behavior is based upon what is the expected time of waiting if he were to join the queue at this point of when he arrives in the system. So, a plausible bulking function based on the expected waiting time, not on the number in the system, but based on the expected waiting time could be this. So, what is his expected waiting time? Suppose if there were n minus 1 customer in the system already in front of him. So, if he includes himself into the system, so there may be n customer need to be served. Each customer takes 1 by mu time. So, n mu alpha n by mu would be the estimate of average waiting time in the system for this arriving customer, right. which can be put into another parameter alpha, and you can use it in the function Bn to have this. So, depending upon this one particular form, right, which is basically based upon n by mu, not just on n, right, because you want to know mu, because it's, see, number of customers in the system alone does not play a role, right. It could be the fact that what is the expected waiting time that may play a critical role. So, that is why Bn should also incorporate mu in some form. That is what, if you think so, then this could be one function, or you can think about many other functions. So, mm1k is in this case also is a special function. That is the first form of impatience. The second form of impatience is reneging, right. They may join the queue, but they retain the right to renege if their estimate of the total weight is intolerable. So, means after some time they may decide to leave the system, right. So, consider a single channel birth depth model where both reneging and the simple balking, which we have considered earlier, is also there, and which gives rise to the reneging function, which is what R of n that we denote, which is basically unit reneges during delta t when there are n customers in the present. So, you are already in the queue, but what is the probability that he will renege within the next delta t amount of time when there are n in the system, right. So, with R0 equal to 0 and R1 equal to 0 is what single channel. So, that is why these two will be equal to 0. From 2 onwards this will start to play a role, right. So, the new process will still a birth death, but with now the death rate will be mu plus Rn. So, the reneging function would be a part of this mu n, whereas a balking would be a part of the arrival component, right. So, that is what you have to remember into this case. So, different functions Rn, right, I can get different mu n's, right. So, now then this is the standard process for getting the stationary distribution. Now, if I substitute in terms of lambda I, lambda n is basically Bn times lambda. So, that B also will be there, and mu n would be mu plus Rn. So, that is what will come here, right. So, both put together, both balking as well as reneging is there in. Now, depending upon what is this forms of this, you can simplify this, you can obtain Pn, and hence you can obtain the other ones, and P naught you can obtain in the usual manner. So, again a good possibility for a reneging function is this e to the power alpha n by mu, right. So, this is reneging behavior. So, you see like where we are tweaking the birth and death rates, right. If it is balking in the arrival rate, if it is reneging is in the death rate. Reneging is this particular concept that he is in the queue and then he leaves. Balking, at the time of arrival he decides whether to join the queue or not. Okay. The other phenomena is this jockeying, which is basically moving back and forth among several sub queues before each of these several multiple channels that we have in the system. This is quite interesting phenomena which you would often see say in airport or in railway station or in bank or in many places, wherever you go, or in supermarket, wherever you go. But this is very difficult to handle analytically because there is no system. You cannot take this analysis analytically beyond a certain point. Maybe 2 channels you can handle to some extent, beyond that it becomes very difficult to analyze, right. So, its general concept becomes very hazy unless you put in rules of he will go from here to there with certain probability and so on, things like that. It becomes very complicated to analyze this behavior, but it is a quite interesting phenomena, but very difficult to capture it, but it is possible, right, but less work is being done on this line, okay, in the jockeying case. This is the 3 forms of impatience that we have here. Now, is there any more birth death queuing models are available that for us to analyze? Remember, what we have seen is only a very small quantity of queuing models that can be modeled by a birth death process. Though we have not done, detailed analysis can be done with respect to each of these models depending upon the requirement. You see like sometimes we consider blocking probability, we did not bother about number in the system for the particular system and so on. But even that, if you want to study elaborately, right, that is what is required if you have a particular system in hand and you want a thorough understanding of the system, then you have to look at every aspect of it in a thorough manner. That is you have to do, right. We just showed you how to derive the performance measures, right. Now, once you have the performance measures in hand, each of these performance measures, you can analyze it with respect to each of these input parameters to see its impact on that particular performance measures. That is how the performance analysis needs to be done. Okay. But that is depending upon the requirement. Okay. But it is similar, there is no difference. But in general, such a modeling framework, meaning the modeling framework based on birth-death process, is applicable whenever the arrivals and departures happen one at a time, right. And since this is the phenomena in most scenarios, so this is also applicable in such scenarios. Whenever this is there, you could have. What we need to figure out, what is the birth rate, what is the death rate. So, once you figure out what are this lambda n and mu n, you have one model. For each type of lambda n and mu n's, right, you have one such model and the analysis can be carried out. So, like this, if you think, then this lambda n mu n is what is basically the modeling one. So, you have to observe from the real system what could be the functional form of this lambda n's and mu n's which would best represent the given system's arrival and departure. So, once you figure out that, then you have the model in hand and you can do the analysis. So, depending upon each of these lambda n's and mu n, you have one model. So, that number of birth-death queuing models is, in that case, collection is very large, right. So, the rates could be linear, quadratic, polynomial, exponential, rational function. There could be many different ways, function that you can extract from the reality which could model the real situation. So, but the more complex the rates becomes, you will lose the analytical tractability in this particular case, but you can find still approximate solutions. If that is not happy, you can appeal to the numerical procedures or even simulation procedures. Numerical procedures is always possible because you have the standard numerical procedures for using this BDPs, right. So, you can always apply the numerical procedures no matter how complex the rates lambda n's and mu n are, even in the case of BDPs, right. So, to get the stationary distribution, mean number in this, once you get stationary distribution, then you get the mean number and all other parameters easily from that, right. So, one can employ numerical procedures or simulation techniques even in certain cases if it is required to get the solution. So, it is possible to handle, it may not be analytically, but the models, the class, the number of models is very large. We have given, based upon the birth-death process, what are the type of queuing models that we can handle it in this system models that we have considered so far, which we call it as birth-death queuing models. Okay. The more general Markovian queuing models is what we might take it up later. Okay. So, we will stop the birth-death queuing models discussion at this rate. What is left is the transition analysis of such thing, which we will talk in the next lectures. Okay. Thank you. Bye.